Hey guys, welcome back to another episode of Everything EE. Today we're taking a look at op amps, finding the V out, the output voltage of op amps, with two unknown input voltages on the positive and the negative terminals of the op amp. So this is a pretty common op amp problem. You have two resistors and input resistors. One of these on VA is 5K, and then on the VB input, we have an unknown resistor, RB, and then we have a divider resistor, or a voltage division resistor, 10K going to ground, and then we have a 10K negative feedback resistor right here. That's coming back from V out. So with these op amps, we know that with an ideal op amp, these two input points at the positive and negative terminals, they want to be the same. They want to equal themselves out. So in an ideal op amp, these two voltages would be the same. So we'll use that here in a bit. Okay, let's get started. The two questions we have here is A, find VO in terms of VA, VB, and RB. So that's going to be our first plan of attack. Then we have a second question here. B is suppose VA and VB are 1.25 volts. They want us to calculate the value RB such that VO equals 0 volts. So they're basically just giving us some givens for our unknowns, and they want us to figure out what RB value do we need when VO is equal to 0. So let's start off with A. So here's A. So with A, we want to find out what VO is. So we're going to use some nodal analysis here. And first things first, we're going to label some points in our circuit. We're going to call this VQ. And like we said that VQ would be on both of these terminals in an ideal op amp. Okay, so with that, we're going to look at this node here, and then we're going to do nodal analysis, and what that will give us is VQ. This is the voltage across the 5K resistor minus VA over 5K. And then we want to go across the 10K. So we've got plus VQ minus VO over 10K. And that's going to equal 0. So let's go ahead and group up these voltages in order to get VO by itself and get our first answer, which will be VO in terms of VA, VB, and RB. Okay, so let's group up. Those for VQ, and then we'll go ahead and group up VA. VA is just by itself, so we'll have minus VA over 5K, and then we have minus VO over 10K. All right, so let's keep going. This equals 0. We can combine these, get a common denominator. That'll give us 3K over 10K VQ. And then we can move the VO term over minus VO over 10K. We can move that over. And VA over 5K just stays the same. So we're going to add it to both sides. So that becomes VO over 10K on the other side of the equal sign. Now we want to get VO alone. So we'll go ahead and multiply both sides by 10K. So this is going to distribute to here and then over here. So we can bring this, let's bring this up to here. And so if we distribute that 10K, then what we end up with is 30K over 10K VQ minus, again, we're distributing the 10K, so we end up with 10K over 5K times VA, and that's going to equal, sorry, I was running out of space, VO. Okay, so then we can go ahead and combine or divide out. This becomes 3, and this becomes 2. So what we're left with is VO equals 3 VQ minus 2 VA. All right, so we're gonna save that. You can tell here that we're almost there, but we're not completely there yet because we have this VQ, and the original question wants these this VO with respect to VA, VB, and RB. So we can tell here we're covered with the VA portion, but we need to take this one step further and figure out what VQ is. So VQ, first we were looking here at this node. Now we're going to look at the node on the positive terminal right here, and we're going to get another equation for VQ using nodal analysis. So draw a line here. We can say VQ minus VB over RB plus VQ over 10K. So that was the second resistor going to ground. That's equal to 0. And then we can say that VQ minus, whoops, went a little too fast there. We'll pull out VQ. So we've got 1 over RB from this term, and we've got a 10K plus 1 over 10K times VQ, then minus VB over RB equals 0. Okay, let's give it some space. And I'm going to go ahead and snake down here. So let me just rewrite this one more time. So we have 1 over RB plus 1 over 10K VQ minus VB over RB equals 0. So let's move this VB over RB term over, and then we will also well, let's do that step first. So we will get 1 over RB plus 1 over 10k VQ is equal to VB over RB, because we added that VB over RB to both sides to cancel it out. And then finally, what we're going to do is we're going to divide by this to get VQ by itself. All right. So if we do that, we'll be left with VQ is equal to, the way we're going to write this term up here, this 1 over RB plus 1 over 10k, we're going, if we divide it, we're multiplying by the reciprocal. So that's going to end up being VB over RB times 1 over RB. Oops. One over RB plus 1 over 10k. And so if we went ahead and distributed out this RB to the denominator, we get VQ equals VB times 1 over 1 from this RB over RB plus RB, geez, sorry about that, plus RB over 10k. Okay, let's bring this up here. Let's pretty this up a little bit. What we can do is we can get this RB by itself by multiplying by 10k over 10k. So 10k over 10k, and what we're left with is VQ equals VB 10k on the top, and then 10k plus it's 10k RB divided by 10k, and that goes away. So then we're left with VQ equals VB 10k over 10k plus RB. So this is our other equation. This is our second main equation. Now we're going to use this. See, this VQ is only using the variables VB and RB, and if you remember, those two variables are what we want in our V out equation. So if we go back up here to this V out equation, equation 1, what we're seeing here is we have this 3 VQ value, and we can plug in equation 2, which defines VQ with respect to VB and RB. We can plug that in for VQ in our equation 1. So let's go ahead and do that. So we've got, let me just rewrite this. This VO equals 3, and we're going to plug in for VQ now. So we got VB and 10k over 10k plus RB, and that was what we got for VQ. And then we have this minus 2VA. Okay. So then what we end up with is VO. And let's distribute this 3 and rewrite this a bit. So VO is 30k divided by RB plus 10k times VB minus 2VA. And then up above, well, this would be our answer for A, because this is in terms of the variables RB, VB, and VA. So this is our answer for A. Right. So let's continue to B. And B was giving us values for V out, VB, and VA. And they're wanting us to find RB. And those values were, we'll just put part B right here. Those values were VO is equal to 0 volts. VA is equal to VB, and those are equal to 1.25 volts. And we want to find out what RB is in this scenario. So let's go ahead and just plug and chug. So VO is going to be 0. We're going to have that equal to 30K divided by RB, which we don't know yet, plus 10K. And then since these two are the same here, this VB and VA is 1.25. You could just take out the 1.25. So you'll have these two together. So we have that here. So we have a minus 2. And then you're able to take out, since these two are the same, you're able to take them out and put them right here. Okay? So then our next step is going to be, we can go ahead and divide this out, this 1.25, and we figure out that this equation is actually not dependent on that. And that's pretty much because of the case that they're both the same. So those cancel out, which is nice. And we end up with 30K over RB plus 10K minus 2 equals 0. So let's add 2 to both sides. Then we get 30K over RB plus 10K equals 2. So now we're looking at this, right? What value of RB can we end up with 2? So if we have 30 in the numerator, then we want 15 in the denominator in order for us to end up with 2. So, we can just look at it, and if we want 15 on the bottom, then we know that RB needs to equal 5K. So this is the answer to B. All right, guys. I hope you enjoyed this example and learn from it. As always, like and subscribe, and let us know below in the comments if you have any questions. You have a great day. So instead of using a nodal analysis on VQ on this positive terminal of the op amp, we can use a really nifty trick that's going to save us a lot of time. I think the nodal analysis part took maybe 5 to 7 minutes, and with this trick, you can definitely get done with this and get VQ really fast using voltage division. So we can see here that in our regular voltage division equation, we would have an RL, the load resistor, and this series resistor RB, and our VQ is our output voltage. So we can write our voltage division equation as VQ, or the output voltage, is equal to the load resistor 10K divided by the series resistor RB plus 10K, the load resistor. and this is all multiplied by the input voltage, VB. And we can see here that this VQ is the same VQ that we got before. That took a lot more math to get to. So using this trick is going to save a lot of time, especially on quizzes and tests when you're under the gun and you need to get finished quickly. So keep this in your back pocket. Look out for those voltage division shortcuts, and hope you enjoyed this video. Thanks a lot. Bye-bye.